Okay, welcome everybody. We had some technical hiccups, so I'm running it now on a Mac, so the fonts will look slightly different. My name is Niels Basjes. I'm one of the lead IT architects at bol.com, the biggest online retailer in the Dutch language area of the Benelux. I'm going to have a talk about Measuring 2.0, a project that started a few years ago as a bit of frustration of the status quo. The overview of the talk is I'll talk a bit about bol.com, what we do, what we use to build those things upon, and what's wrong with that. And then I'll go into Measuring 2.0, the next generation thing. That also includes a lot of real-time streaming parts based on Apache Flink nowadays. Okay, bit of background. I have a master's degree in both computer science and business. I've had various software development, research, and architect roles, and I'm a heavy contributor to a lot of the big data projects, and I'm a committer of Apache Avro. So what is bol.com? Like I said, biggest online retailer in the Dutch language area. To give you a bit of sense of scale, our catalog is in the 14 million items, of which about 11 million are available for sale right now. 6 million active customers, tens of millions of active visits each month. Our number of page views per year is over 2.5 billion. And it may not be surprising to you that we've been using Hadoop in production since 2010. The main application we use it for is personalization. We want to make the customers happy, help them visiting our website. And the first thing we built back then was search suggestions. When you type some letters, you get suggested search terms. That's based on click traffic by customers. Nowadays, we also look at your purchase history, what you looked at, what you put in your shopping list, and what you didn't buy. So if you look at the homepage as a regular customer, there's a lot. This is based on what I call Measuring 1.0. Well, there are some issues with that. And the biggest one is that the data arrives in blocks of 24 hours. So the personalization is the day behind. When we know what a better recommendation is, the customer has already left, and we have to hope they come back. And as you may know, the value of data decreases rapidly with time. And what you would want is to stay in the low minutes, maybe even seconds range, to give feedback, to help them. The measurements are done using JavaScript. So we have this kind of stuff in the HTML. And as you see here, there are variables. They're called evars and properties, and they're limited. It's heavy on the client. We cannot measure everything, and they're unclear. So what happens also with the limitation of the evars, they get reused. Depending on the page, some evars mean different things. Makes it very hard to use the data for our data science guys. Data is incomplete. It's inaccurate. Sometimes the JavaScript is slow. And it's important to realize that this technology puts everything in the URL. Now, a product, the description we use for a single product looks something like this. And the worst case I've seen over the years is this thing. It's our all deals page, all the things we are actively promoting at a point in time. And this one had 34 of them throughout their website. And that resulted in this baby. If you put that in a URL, things break. They really do. So you miss data. As you may understand, things needed to change. And our business goal was that we wanted to be able to know exactly what was going on the web shop right now, because we wanted to assist the visitors right now. So while the visitor is still on the site, we want to give them the best experience possible based on everything they've done so far, including the last few clicks. But in addition, some processes, in terms of their algorithm, are batch-oriented. And even those we want to run multiple times per day. Things like search suggestions, search rank, the sorting of our products, and recommendations. So that's why I started the project, which we now call Measuring 2.0. And it's really all about making better measurements, being able to process them faster with lower latency, and as a consequence, making applications more relevant. So the goals are really high. I just want everything. All interactions, all users, even Googlebot, because they don't do JavaScript, all the details. I want to know exactly what was on the page. I want the data to be more reliable, lower load on the clients, and the lowest possible latency. So just, everything. But in addition, because of the complexity of making these measurements, I want it to be a lot easier for the developers. And I also want to allow business people to ask new questions we didn't think of before. Okay, but over time, over the last few years, the laws have been playing a part of this. Nowadays, we have privacy laws that say you can't do profiling on data for more than 2 years. Of course, security don't want us to record security-sensitive stuff. And on the other hand, our data science guys want to do profiling on multiple years. Recommender system we have currently uses over 5 years of clickstream data, as an example. So how do we solve that one? Well, let's start with measuring everything. When I mean measuring everything, I really mean everything in terms of the interactions. So regular web analytics, they measure the page, just the page, and then maybe what kind of page it was and who visited. But what I want to know is all the parts of the page and why they were put there, and what was then put in. So, for example, in the bottom right, you see a block of recommended products. I want to know that that group was there because it was a recommendation and not some kind of campaign. Cause and effect in these events is the most important thing for us. If you look at the type of analytics we do, the type of applications, it's banner optimization. You show something, they click or they don't. A/B testing, same thing. Search suggestions, look at the search term in relation to what people did with it. Attribution modeling, the banner in terms of what people did with it. So it's all behavioral analytics. It's all cause and effect type of processing. The high-level data structure I designed for this project is therefore a very simple record that has an entity and the effect on that entity and a cause. And that cause, on the other end, you also have hooks, in terms of website, things you can click on, usually add to cart, go to a product page. And so if I have a cause, a reason for entering the website, maybe a banner, I record a bunch of things. These are the products I put on the page for various reasons. And then somebody clicks. Okay, I know which one they clicked, and I know what the consequences were. And that continues all the way up to, hey, I bought something. And now, because I have all the causes, I can trace it back to the root. And I can also trace which other things competed and which one. Okay, so that's the high-level cause and effect data structure. How do we get these measurements? Because that is also a bit of a challenge. The JavaScript is really bad. Now, if we look at how can we measure, if we take the basic high-level technical process, it's the browser doing a request through the web server to the application server and the response going back. Doing it in JavaScript means you know what really happened on the browser, but the quality of the data is really poor. If you use the Apache access logs, for example, you actually only know at URL level what happened, but you don't know what was in there and why it was put in there. If you dig a little deeper, some tools support sniffing. So you extract the HTML, so you can know in detail what was put in there, but you still don't know why. The only place you know why is at the application server level. So what we chose as an implementation strategy is to do a hybrid. Measure as many details as possible at the application server level, tag everything with an ID, and then those IDs get shipped to the browser where we know what happened to it. And in case of users like Googlebot, we don't know what they did with it, but we know the user agent, so that's fine too. We still know exactly what we shipped to them. And in case we do stuff on the client side, it has to be as lightweight as possible. We do as few things as possible there. So that will give us a data. So we have the data, we have the event stream model. How do we process it? Okay, remember we said, hey, for online situations, we want to be in the low second ranges. We want to have long history. In offline, we want to do incremental batches. Hey, that sounds familiar. People call that Lambda architecture. That sounds really good. But the nasty thing about Lambda architecture is that it is about combining the real-time and the batch part at query time. So far, so good. But if you look at all the papers and presentations about it, most of them, as far as I've seen all of them, they say you cut the boundary between those two at a specific millisecond. And if you do that, you cut the streams. You cut the cause and event streams. That is fine if you're Twitter, where everything is a single message. That's not fine for us. Because if this is an idea of the traffic pattern, and these streams are the visits, cutting it at the daily basis at the quiet point of the day, you cut only a few. If you want to do batches every 15 minutes, you get this. This results in data that is near impossible to process for our data science guys. So a few years ago, I sat down and I made a really complicated design, and I call it the Sessionized Lambda architecture, which is essentially the Lambda architecture with a few additions that I don't see in other presentations. And the first one is bounded event streams, the cause and effect relationship, because that is paramount for us. Queries take time. Something I also miss is the fact that everywhere I read, they assume queries take 0 seconds. So there is no locking between expiring the data from the real-time part and et cetera. You need that. And service orientation. A few years ago, I introduced microservices at our company, and everything we build has to fit in there. We have to fit it in such a way that other people can build applications on top of it. Now, as you might understand, in terms of web browsers, there is a few terms I need to explain, otherwise it's hard to understand. The browser is something that is installed on the computer. Now, if you open it and visit a website, you usually get a cookie with a unique ID, a session ID, but that stays active for weeks. People don't close their browser anymore, they suspend them. So the value is retained over a long period of time. Now, as I said, I need bounded streams. So I have to enforce a bound, and that's what I call a visit. If you're inactive for 30 minutes, I cut it. And if you're active continuously for more than 12 hours, you're not human, so I can cut it. And most cause and effect relationships are really only interesting when it's a human. So this is fine. So everything we do is towards building these visit streams. So how do we process that? Okay. The high-level design I came up with, and this is actually the thing I'm building and I'm testing right now, is that new events arrive from the measurement infrastructure, which I'll show in a few minutes. Then I have some kind of administration about the active visits, people actively on the website and when they started and have been active for the last time, etc. That visit ID is generated and tagged onto the measurement. Those go out in real time via Kafka, so others can use the real-time stream with the visit IDs. But they're also persisted in a buffer, and in a time every so many minutes, I extract the visits that have been completed into files. Those get stored in HDFS, so you can do large-scale queries and analytics on that. In case you want to build an application against this that actually implements the full sessionized Lambda architecture, it will look something like this. And the query boundary you see here is an administration of which visits are still in the stream and not yet in the batch layer, and vice versa, and all the locking that has to do with querying and expiring those things. I have it designed. I'm not going to build it. It's too hard. Nobody needs it. Because talking to all the other people that build applications, what I see is that most only need the real-time stream. In case they want to do stuff with long-term history of a customer, of a visitor, we can have a small aggregate pre-computed, which is maybe 1 or 2 kilobytes, with the products they're interested in, the categories they're interested in, and things like that. And just load them in memory in the stream component as soon as you see the first event with that customer ID. And of course, you have the batch operation processes that now can run every 15 minutes. Now, the privacy thing I mentioned earlier is a bit of a question. How do you handle that? How can you do the privacy analytics at long term? Now, privacy protection says identifiable data cannot be used for personally identifiable profiling over more than 2 years. And that is really about data elements that you can use to point to an individual, like IP address and customer number and things like that. But what is profiling really over long term? It's looking for behavior patterns, because the personalized things lose value when they're more than 1.5 years old. Then they're not as relevant anymore for the behavior patterns of that visitor. People change. And after about a year, it becomes less relevant. So this is only about more anonymous profiling. And the query pattern you see in those kinds of analytics are usually about group by customer ID, because I want to know what that person did over a longer period. But if that's the real question, then these queries give the same answer. Because if you encrypt it, or you hash it, or even salt it and hash it, the group by will still yield the same result. Hash collisions, and hash collisions are, if you look for large-scale patterns, are not important. So what we chose is that for the data in motion, the streaming stuff, we persist that in Kafka, and that expires after a couple of weeks. And for the data at rest, the identifiable ones are simply deleted. And the anonymous ones are salted with a yearly salt. So in our IT operations, we have a system that will have a secret salt. Everything gets salted with that, hashed, and we only persist the hash. And nobody, not even me, not our data science guys, have access to the salt. So nobody can reverse engineer it. And by splitting the access permissions between the two, we keep that safe. So what gives us that is that on named individuals, we can do analysis over the last 2 years. But anonymized, we can do analysis on a yearly basis for much longer. But it's anonymized, and you still have all the details to do the real business value analytics. So how do you build something like this? Well, the design I created is, I'm going into a little bit more detail now, is that we're going to introduce a several measuring components into our web front end. Part of it is in the application server that records the details of what and why, and puts that in Kafka, and puts the IDs of those measurements in the HTML that are then, via JavaScript, put back also into Kafka. That is mostly about what was put on the screen and what was clicked and things like that. Then the Sessionizer, which I showed you just before, with one extra thing, and that's GeoIP. We would like to know what country that visitor came from. Was it Netherlands, Belgium, Germany, US, whatever. Just the country code. And we output that, as I showed earlier, in Kafka and as files. This part is the personally identifiable stuff. So from there, we have an anonymization filter that anonymizes it and outputs the same data, anonymized, also in Kafka, and also as files, and those can be then used for dashboarding and for recommender systems and things like that. Now, a couple of years ago, I started my first prototype to build this. This gives a good impression of what it was like, because I tried it at that time with using Apache Storm. Stream processing, low latency, lots of people using it. Sounds like a plan. Until you try to do it back then. The API is, for me, really unfriendly. This was actually copied and pasted last week from their website, so the API hasn't changed much. You have to make sure that the names of the bolts all match, otherwise it simply doesn't work. It's an at least once streaming thing. If you need exactly once, you go to Trident. If you go to Trident, you go to micro-batching, and that means latency much more than I want. And Storm, when I tried it, is completely stateless. Now, a few weeks ago, they said they now have stateful things, but the thing I tried is completely stateless. So building in the state of the visits is incredibly hard. And at that time, it was said, you can run it on Yarn, but I never get that to run. Perhaps that now works, but back then it didn't. So how about Spark streaming? You know, lots of libraries and tools, a very good toolkit, but also micro-batching. And I don't want that latency. So then came last year at Berlin Buzzwords. I talked to Stefan, and I asked him some questions, because I already had quite a bit of experience in doing it with Storm. How does it work in Flink? Well, Flink is also low latency, but it's exactly once. And that is mainly because it has the recoverability of the state built in. And it runs on Yarn. And the state managed in the framework also supports all these checkpoints and save points and things that make it easy to recover after a failure or restart of the application. What's also really nice is that it has a concept of windows. A window is a group of elements that you can combine into a streamingly built up batch, which makes it really useful for the type of analysis I want to do. And to me, this feature, event time, is the biggest plus of Flink I've ever seen. It means that if you bring down the application for, say, a day, extreme case, and you bring it up again, so it reads from Kafka, then all the events of timing out the 30 minutes and the 12 hours are based on the time in the data. So you can process a day worth of data in maybe, I don't know, 20 minutes, and still have all the timeouts correct. That is the biggest plus of Flink. There are challenges. The first one I ran into was reading and writing from HBase on a secure cluster. So I fixed that. And we still have the problem that after 7 days, the Hadoop delegation tokens time out, and then any job dies. Also, the Spark jobs we run on the cluster, they just die after 7 days. It's a setting, but still, it's a finite time. And my windows, the data in my windows is too big to fit into memory. So right now, I'm shoving them into HBase. That's what I have in the graphs a little later also. But I have to evaluate the RocksDB, which is in the newer versions of Flink available. Also, very careful, the exactly once is on the processing and on the Kafka input, but not on the Kafka output. In case of a distortion and a replay of some events, you get duplicate events in the Kafka output. Something to be aware of. So how do I assign the visit IDs in stream? The window implementation buffers until the window is complete and then flushes it. So that's too long. So I had to build my own custom operator. I had some help from the data artists guys. Thank you very much for that. So I built that. And how does that look? Well, there is the assigned visit ID operator that receives the events, has a bit of state, and shoves them out again. Then they're stored in HBase and in Kafka, and then through an anonymization filter, and they're also stored in HBase and Kafka. Then the watermarks arrive, and based on the watermarks, I say, hey, there is an expire of this visit. I time it out, and I send out an end of visit event. Those are then grouped in a window to avoid too many files on the Hadoop cluster. I group the end of visit events. And then when I have a window of ended visits, I pull out all the events from the HBase and I store them in Parquet files. When I started, I made this design. And then when I started to build it, it turns out that you can only have one output type of an operator instead of two. So I had to do some stuff. And the watermarks are really, really important. So what I ended up building is, well, this is the same, but I had to multiplex them because one type of output. And then they go out. And then I pull out the ended visit events again. And there I had to generate new watermarks. Because without those watermarks, the windows don't work. And from there, it's more or less the same. While building this, I realized that those end-of-visit events may be useful for downstream applications, so I decided to keep them in. If you're building something like this, debugging the watermarks is essential. And it turns out that they're quite tricky to get right if your data is too messy. So that's not a Flink problem. It's really how clean is your data. So I needed to do some debugging of the combination of the watermarks and the events. And to do that, I wrote a very simple operator that simply prints them. Because in an operator code, you can process watermarks and process the events. And all it does is prints them to the console for development purposes. Now, if you're building a streaming application, you have to realize that requirements will change. It happens. And what we do is we use Apache Avro, the IDL schema language, to define the schemas. And that is nice because it generates really usable Java classes, and it supports name-based schema evolution out of the box. So if you have a class with if you have a record with a newer schema, you can simply read it using Apache Avro in the newer situation. We have chosen Parquet to persist the data in files. Because I'm writing the event streams on a per session basis or on a per visit basis, what you see is in that range, they all have the same IP address, same user agent. Most of them have the same customer number, and a lot of attributes are all the same. So using the column-oriented Parquet format makes that compress really, really well. Also, Parquet is supported by the tools we use to read and query again, so that's also a big plus. And writing Avro records into Parquet files is really easy because Parquet has actually has support for that. Now, in the streaming scenario, we use Kafka, like I mentioned. So it's a high throughput, low latency transport pipe that persists the data for a couple of weeks. So how do we put that record we have as a byte array in Kafka? OK, how do you serialize that? The important thing to realize is that Apache Avro needs the original schema to deserialize a byte array again. So you need the original schema. Now, in the test case I'm running right now, the original schema is like 10 kilobytes, and the record is like 400 bytes, and I don't want to attach the entire schema to every message. So how do you do that? Because the schema will change. If the schema changes, and you have like, say you persist the messages for 4 weeks, and you have 2 weeks of old schema and 2 weeks of new schema, and you hook up a new application, it must be able to read all the records. How do you do that? Well, that is something I'm working on right now. It's an Avro project where I've said I'm going to make a wrapper around the normal serialized Avro record that I call a message, which essentially contains the fingerprint of the schema. Now, if you combine that with a pluggable schema database, which you can do in, well, any system, really, maybe a property file, maybe a Redis or whatever, then you can store all the versions of all the schemas in there and retrieve them by fingerprint. So any consuming system can then deserialize the record and read it in their local version of the schema. Now, this at Bol.com, we have been doing these big data things for quite a while. So you may realize that at ours, this is not a hype. This is what most of our teams are required to do. Most of our development teams use HBase and the Hadoop cluster to do part of their work. So if you think this is cool, don't hesitate. Join us, contact me, and we'll talk. Questions?
Hello.
Hello.
Thanks for the talk. So I have a question regarding this hour schema. Why don't you guys use our registry for storing your schema?
Sorry?
Our registry, schema registry for storing your schema. There is already built one in.
Yeah, I think Confluent wrote one.
Yeah, Confluent.
Yeah, I know. I know, but for now I'm saying that within the Avro project, I'm making it pluggable. So if somebody says, I want to use the Confluent implementation, they can. They can simply attach it to that pluggable interface. But if somebody says, no, I just want to use property files, or I want to use a proprietary thing like we have internally, then that becomes also possible. So I want to keep that a bit more flexible. And something I'm also building in to keep it a bit more flexible is that the actual serialization of the message body, I want that to be pluggable also in order to support encryption. So if somebody says, no, I want to persist all the streaming messages in an encrypted form in Kafka, that is also possible. It's still a work in progress. It's not yet finished, but I'm working on it. Yeah.
Hi.
Hi.
You said you had to put the state into HBase. So what was the size of your Windows state on each worker?
Okay, I did some calculations because I know the traffic level of our website, and the estimate is that we have to keep we will get something like 50,000 events per second during the peak of our season. And the events are, in the experiments I'm running now, they're about ½ kilobyte in size each. And then with all the timeouts taken into account, that runs into the too many gigabytes in RAM, that is. So that's why I'm saying I have to persist it to disk, or I have to convince the boss to get a lot more servers to keep it in memory. But you know, persisting it to disk, and I'm doing load tests using HBase, that works quite well.
Hi.
Hi, Stefan.
Hi, Niels. Thanks for the talk. Quick question on this, like security and expiry of the access tokens. What do you actually do to work around this? Do you have something like a script that periodically just makes sure the job is completely killed and restarted, so it acquires new tokens?
Yes. The timeout set for the Hadoop delegation tokens is 168 hours. That's the default setting in the Hadoop cluster. It turns out, for a very strange reason, that the jobs die after exactly 173.5 hours. So that's 5.5 hours later. And it's so exact that I've run the experiment several times, and they all die within a range of 30 seconds. So for some reason, that's the cutoff point. And what we have now is for the Flink jobs running on our cluster, we have picked a point in the week where it's most quiet, and there we simply kill them and restart them. So that's once every 168 hours, so we have a bit of room to spare. And because we control the restart, that works quite well for now.
Are you actually using a save point or so to resume from the previous execution after you basically kill it and restart it, or do you basically let it pick up a clean slate?
The applications we have right now in production don't use Windows. And in those specific applications, which are background analytics jobs, losing 1 or 2 records is not that much of a deal. So at this point, we don't use it yet.
Okay. And then maybe a final remark. I'm not sure if you've seen it. There's actually a thread that is dealing exactly with this, like Kerberos tokens and an expiration and so on, we're trying to add some functionality to attach key tabs to a job so it will actually automatically renew these things.
Oh, excellent.
Hopefully going to be in a few months.
Okay, sounds good. Thank you.
Thanks.
Hey.
Hi, Steve.
I suspect I know why your tokens are expiring a bit after that time is because they do the renewal in advance and 12.5 hours later it all dies.
Okay.
As someone who has painful experience of a Kerberos and a yarn, I will say that actually what you should do is ask the Flink people to do some token renewal, which can not only be done with a key tab, because people hate key tabs around, but actually just have something push out fresh tokens from your desktop or Uzi or something like that. That's what other people do.
Okay, thanks.
Have you thought about an end-to-end way, an end-to-end idempotency way to get exactly once output for the Kafka sync?
I have thought about it. I put up my idea on the Flink user list, but that would require quite a hefty change in the output, because the idea I had is that when you output messages into Kafka, you record in the output sync in terms of state where you left periodically. And then in a recovery scenario, you would have the sync act as a client and read in till the point where it sees the message that it has to output next. But that would be a bit of a hefty rewrite. And I haven't taken the time yet to try to build that yet. But if you feel like building it, please do. It would be useful to everybody.
Thank you.
Then, thank you, Niels.
Okay, thank you very much.